So, we have said in the last session that from this session we will talk about differentiable functions. So, before that let us at least recall the notion of continuous functions. So, suppose I am assuming you know the words continuous and differentiable, may not be the meaning of them, but you might have seen that before in 11th 12th classes that differentiable function is a continuous function with extra properties. So, let us recall what is a continuous function, and let us recall the notion in terms of limit of a function. So, u is subset of R and f is a map from u to R. We say f is continuous at a point a belongs to u if something happens in terms of limit. What is it? Limit x goes to a, f of x is equal to f of a. This is what we wanted to happen when we say that f is continuous at this point a. Now, maybe you might already know the definition of this limit, but let me recall what it means. So, what it means is the following, that this is some number a, let me write down, a belongs to R with some property. What is the property? That I have said that a is an element of u. So, an element a is said to be limit of f as x goes to a if some conditions are satisfied. What is the condition? For any sequence xn in u that converges to a, we should have f of xn converges to a. This is what we mean when we say limit of x goes to a, f of x is equal to a. This you might already know. Now, let us change the base point. Here we are talking about a. Let us change the point slightly. You will see why we are doing that. Let us just slightly rewrite this definition. We do not want to give a reference point as a, we want to give a reference point as something else. Further, we need to make some small computation. So let us do that. So, here we are saying that xn is a sequence converging to a. This says the difference xn minus a converges to 0. So, now, when we are talking about limit x goes to a, we took a sequence that converges to a. Here we have a sequence that converges to 0. So, we would be getting some notion of this form, limit h goes to 0, some function. What is the function? See, observe that these elements are elements of the set u minus a. I am not saying u from set u we are removing a, no, not that, we will be writing as u this minus this symbol. This symbol is for removing some element, this symbol is for the difference of two sets. So, here we are talking, see here I am taking xn minus a, so it is a element of u minus a. So, now from the function f on u, we construct a function g on u minus a. How do you think it should be defined? An element in u minus a is of the form x minus a, we are sending it to f of x. See, x belongs to u, so f of x is an element of R, we are just considering this function. So, why are we doing this? For the function f, to talk about limit of f as x goes to a, we have a sequence in u, we have a sequence xn in u that converges to a. Now, this difference converges to 0, so we have a sequence in u minus a that converges to 0. So, we can talk about limit of some function defined on u minus a as h goes to 0. This may be defined, may not be defined, that is secondary, but we can still talk about that notion. So, here this box that I mentioned here, I am replacing that by this g of h. So, the whole point is I do not want to talk about limit x goes to a every time. I want to change this reference point to 0, that is why this small change we are making. Now what? Now the question is, see from f we considered a function g, and g is related to f in a very nice way. Now the question is, suppose I know that limit of x goes to a, f of x exists, then can I say the limit h goes to 0, g of h exists or not. I leave it to you to check that these two, this exists if and only if this exists, and they are actually same. The more details are added in the lecture notes. But before saying that, you can just check. You can just write down the definition of a limit of a function as x goes to some point. Then see if this exists, then this exists. See, this is the very simple function. I am only writing same thing as f with a slight change. So these two should be related ideally, and I am saying they are same. So limit h goes to 0, g of h is equal to limit x goes to a, f of x. For this, f need not be continuous. All I need is I want this limit to exist, that is all. Now, as I said, we are starting at the point where f is continuous. So this is actually same thing as f of a. So here I am writing this as f of a. By the way, what is g of h? We defined g for elements of the form x minus a. What about an arbitrary element h? Any element h is of the form x minus a for some x in u. So if I am writing here f of x, I should know what x is. So what is x from here? This is same thing. This implies x is equal to h plus a. So instead of f of x, I will write f of h plus a or a plus h, whatever. So limit h goes to 0, f of a plus h is equal to f of a. Now see, this is not very different. I am just changing the reference point from an element a to element 0. See, on the left side, this function has a h component, and we are talking about the limit. Here there is no h component, so one can just pull it to the left side, and h goes to 0, f of a plus h minus f of a is equal to 0. Now the nice thing about this is, first of all, limit of something is 0, that is first nice thing. The second thing is, the reference point is now 0, irrespective of what point you are talking about. Even though this irrespective of what function you are starting with, at the end you have a difference. Now this is the function of h, a is fixed. Now this is function of h, and limit of h goes to 0, g of limit of h goes to 0, f of a plus h minus f of a is 0. This is true for any continuous function f at the point a. Now let us think about functions whose limit is equal to 0 as the variable. So this is function of h now. Now we are looking at functions, say limit h goes to 0, g of h is equal to 0. We are looking at functions g for which if the variable goes to 0, then the limit goes to 0. Now one obvious example is one obvious collection of examples are polynomials with no constant term. For example, let us take g of h is equal to h square plus 2h. Now what is limit of h goes to 0? G of h, this is simply 0, h goes to 0, this is 0, h goes to 0, this is 0, so the sum is 0. So the polynomials with no constant term are some examples of functions satisfying this property. Now we are looking at functions so that this corresponding this new function satisfy the same property that are satisfied by polynomials. So now what we ask is the following. See, look at polynomials which does not have a constant term. Those functions has an extra property. What is the property? Even if I remove the h component from all this part, say g of h by h, even if I remove the h component, the result will still be a nice function, so that the limit exists. Limit h goes to 0, here I should put, here I am just pulling it here. So limit of this function exists. This is true, but it is not relevant here, but limit exists. So the polynomials with no constant term are nice in this sense. Even if I remove the h component from the whole polynomial in this sense, if I take gh by h, the limit still exists. So now this is what we want to have for this difference. For f of a plus h minus f of a, we want it to satisfy this property. In the sense, we want limit h goes to 0 f of a plus h minus f of a by h, we want this limit to exist. So on what basis we are asking this? We know that, see, for any continuous function we have this property that limit h goes to 0, this difference is 0. Now we are looking at functions that satisfy this property irrespective of the function f. Some examples are this: polynomial functions. For those polynomial functions, we observe that even if I remove the h part, that is gh by h, the limit still exists. So now we are asking that we want the same property for this function that we have started with. So we are just replacing gh by f of a plus h minus f of a. Then we are asking that this limit should exist. If the limit exists, then we say f is differentiable at a, and the limit we are denoting by f dash of a. So this is what we mean when we say the function is differentiable at a. So let me just recall quickly what we have done. So for continuous functions we have some property. What is the property? The function that we construct by fixing this point a has this property: limit h goes to 0, g of h is equal to 0. What we are asking is, we are asking that this result, the resultant function, here it is f of a plus h minus f of a, we want this function to be slightly more nicer, in the sense even if I remove h component, in the sense gh by h, the resulting for the resulting function limit should still exist. That is what we want, that is what we have written here, that f of a plus h minus f of a, limit exists for this, limit is 0 every time, then for this fraction the limit should exist. It need not be 0, that is not the point, here it is 2, right, it is not 0. So we just want the limit to exist. In that case we say that f is differentiable at the point a. If I have a function f from u to r such that for every a belongs to u, f is differentiable, then we say this whole function, this function is differentiable on the domain, or we simply say it is differentiable. That is it. Now in case of continuous functions, we mentioned about we mentioned some symbol for set of all continuous functions. Cu is a notation for set of all continuous functions on u. I mean the range is still R, range codomain, whatever you want to call, it is still R, but the domain is u. So for differentiable functions we use some terminology, we will write as du. Du is the set of all differentiable functions on u. Now whatever I have done for continuous functions, we will try to do the same thing for differentiable functions, in the sense that given two continuous functions, we know that the corresponding sum is a continuous function. If I take two functions f and g from u to r, both are continuous, then their sum is continuous. So here we will see, if I take two functions on u that are differentiable, do I know that the sum is differentiable? This is plus, let me write down this clearly. Do we know if the sum is differentiable? So let us try, let us fix a point a belongs to u, and let us see if f plus g is differentiable at this point a. So further what we need is, we want the limit, the following limit to exist: f plus g of a plus h minus f plus g of a by h. We want this limit to exist. So this is a function, this is a point. So this we are writing as limit h goes to 0 f of a plus h plus g of a plus h minus f of a minus g of a by h. I am just combining this with this, then this with this, we get the following. Limit h goes to 0, f of a plus h minus f of a plus g of a plus h minus g of a by h. Observe that this should remind you something about differentiability of f at the point A. So, what is it? Maybe I will just split this into two parts. So, this plus I am writing in between, right. This should be clear. I am just splitting h into the h into h. I am writing down h separately for this and for this. Now, this is a function. I know that limit h goes to 0, this function exists. Limit h goes to 0, this function exists. So, limit h goes to 0, the sum should exist and the result is just limit of this plus limit of this. What is limit of this? This is simply f dash of a. What is limit of this? It is simply g dash of a. So, if I know that f and g are differentiable at a point A belongs to u, then the sum is differentiable at this point A such that f plus g, see we said that if this limit exists, then we are calling that as f dash of a. So, for this the limit of f plus g, this limit for the function f plus g exists, and that limit should be, we should be calling that as f plus g dash a. What we have is f plus g, the derivative at a is simply f dash of a plus g dash of a. So, this is one property. So, we are not just saying that this is differentiable, we are also saying that what is the derivative of that point, the derivative of the function at that point, that is simply derivative of f at that point plus derivative of g at that point. Okay. Now let us do one more thing that we have done for CU. In continuous function we have done that for two functions that are continuous, their sum is continuous. So, the corresponding thing for differentiability we have done just now. For two functions f and g that are differentiable, we have seen that the sum is differentiable. Now, given two functions, the difference is given to continuous functions, the difference is continuous function. So, is it true for differentiable functions also? Given two differentiable function, is the difference a differentiable function? So, all I need to do is I need to put minus here, put minus here, put minus everywhere. Now it is plus, now it is minus, and now it is minus, now it is minus. So without there is not much change. The same proof, replacing this plus here by minus, you will be able to see that given two differentiable functions, the difference of that is a differentiable function such that the corresponding derivative is just the difference of the corresponding derivatives. F minus g dash a is equal to f dash of a minus g dash of a. So, this is same as that of the addition of two differentiable functions. Now, what else is there for continuous functions? Given two continuous functions, their product is continuous, right? Given f belongs to Cu and g belongs to Cu, f times g is an element of Cu. This let me write down clearly. So, let us see if f belongs to if f and g are differentiable functions, does it imply the product is differentiable function? That we will see now. So, further what we need to see is limit h goes to 0 f g of a plus h minus f g of a by h. How is this defined? This is f g of a plus h is f of a plus h times g of a plus h. This is the product of two functions. So, let me write down that limit h goes to 0 f of a plus h times g of a plus h minus f of a times g of a by h. Now what do I do? I cannot take g of a plus h as common for these two. because there is no g of a plus h here. If I am able to take common this component, then I will have f of a plus h minus f of a by h, and that limit exists, then we are done. But that option is not there here. So what we do is we will just try to add and subtract some component. This you might have seen in previous class also. So what we are doing is f of a plus h, g of a plus h. What I want is I want to take one of these as common and get the limit that I already know, f a plus h minus f of a by h, or g a plus h minus g of a by h. I want to get something. So let me add f of a times g of a plus h. I mean, I cannot add simply, I have to just remove that also. F of a times g of a plus h, and I am keeping this as it is. So minus f of a times g of a is this whole thing divided by h. Now observe that these two components has g of a plus h as common, and one nice thing about the remaining thing is these two components has f of a as common. So in these two I take g of a plus h as common, in these two I take f of a as common. So what I get is the following: limit h goes to 0, f of a plus h minus f of a times g of h plus f of a times g of a plus h minus g of a, this whole thing divided by h. Now whatever I have said we have done before, we do the same thing for this also. We just split this h in these two sums. So we have limit h goes to 0, f of a plus h minus f of a by, and there is a g of h component also, g of h plus f of a times g of a plus h minus g of a by h. Now see, if I want to apply, if I want to write down that limit of this and this is same thing as limit of this plus limit of this, I need to know a priori that limit of this function exists and limit of this function also exists. How do I know that? I know that limit of this function exists and limit of this function also exists, right? G is continuous, G is differentiable, G is differentiable, so in particular G is continuous. So yeah, just a minute, there is some typo here. This is supposed to be a plus h, this is supposed to be a plus h, this is also a plus h. Yeah, now this is correct. So here I know limit of this exists because if it is differentiable, so this limit exists. I know G is continuous at this point a, so I know this limit exists, and that is same thing as g of a. Now for this I need to know limit of this function exists, this is constant function, so this limit already exists. So and I know this limit exists, that is just g dash of a. So limit of this plus this is equal to limit of this function plus limit of this function. As I said, what is limit of this function? Limit of this times limit of this. Limit of this is f dash of a, limit of this as h goes to 0 is g of a, plus there is no limit here, that is just a constant, so that I am just writing as it is, f of a, limit of h goes to 0, this is g dash of a. So what I have is that for the product also, for this product fg, this limit exists, and that is same thing as f dash of a times g a plus f of a times g dash of a. So let me write down that once, is equal to f dash of a g of a plus f of a g dash of a. This is the relation between derivative of fg and derivatives of f and derivative of g. Now just like in the case of sum of two differential functions, this computation showed that the product is differentiable Not just that, it also gave what is the formula for derivative of the product of those two functions at the point A. Now what is remaining? Sum is done, difference is done, product is done, product multiplication whatever you want to call, and what is remaining is the modulate inverse. So suppose f is differentiable and nowhere 0, only then I can talk about the 1 by f. Now I am checking for the derivative, or checking if first of all we need to see whether this is differentiable, and then see, just like in the previous cases, here we got the formula for the derivative, not just the existence, we got the formula for derivative, here we got formula, and here also we got a formula for plus and also for minus. So let us first see whether we can conclude about differentiability of 1 by f, and then see whether we get a formula or not. At least we will try to see the existence first. So now I am looking for 1 by f dash a is element of u. For this to make sense, we need to know that this limit exists, 1 by f of a plus h minus 1 by f of a by h, this should exist. This is same thing as limit h goes to 0, 1 by f of a plus h minus 1 by f of a by h. So some small computations, there is nothing serious here. This is f of a times minus f of a plus h by h times f of a times f of a plus h. This is I am just simplifying this into this. This difference is except this is the whole thing, this is the difference. Now there is a h component, so I am just putting h here. Now what? This should remind you about derivative of f at a. What is derivative of f at a? Limit h goes to 0, f of a plus h minus f of a by h. So it looks like this is related to f dash of a, but there is some extra terms. What is the extra term? First of all, this minus should actually go here. So what we do is we will just put some minus here, make it plus, make it minus. So that problem is gone. So we have a plus h, f of a plus h minus f of a by h, that is related to f dash of a. Then there are two parts. Let me just move it slightly so that we get some place. Now there are two extra parts. I don't know what to do. This is constant, so we can just remove that. We can just pull it back. So I am removing this constant. See, this is about a limit as h goes to 0. So this constant doesn't really mean anything, even if it is inside or outside. So I am writing this as minus 1 by f of a. Whatever I removed from here, I just kept it here. Now what else is there? Now I have this extra component, but we know what is the limit of h goes to 0, f of a plus h. What is it? Simply f of a, because f is continuous at a. So limit h goes to 0, f of a plus h is same thing as f of a. Then we use the same previous formula. If I am talking about limit of product of two functions, this is product of two functions. One function is this, one function is this. I know limit exists for this function, limit exists for this function. So limit exists for the product of these two functions. The limit is limit of this times limit of this. This is 1 by, we should be thinking it as 1 by. So now this is minus 1 by f of a times limit of this function is f dash of a, limit of this function, this is 1 by f of a plus h is 1 by f of a. So we have two parts actually here. So this is f of a square, and there is the minus f of f dash of a. So what we have seen is 1 by f is actually differentiable, and the derivative is given by the formula 1 by f derivative at a is minus f dash of a by f of a square. That is what I have written here. Now I should tell you something nice about the differentiation formulas. Suppose I am given that f is differentiable and that is nowhere 0. We have just now seen that 1 by f is differentiable with some derivative. Now suppose we didn't do this computation at all, but somebody said that 1 by f is differentiable and they are saying it is for sure differentiable. Can you compute the derivative? That is the question. The f is differentiable, that is given. 1 by f is also differentiable, that is also given. The question is, can you compute 1 by f dash a? Knowing that f is differentiable and 1 by f is differentiable, can you compute this derivative? That is the question. Now we do not know how to compute the derivative of a single function yet. So it is unlikely that we will be able to succeed trying to do this. So let us do some examples first, then we will come back to this. So maybe a simple example first. So consider the function, the constant function f of x is equal to 9 for every x belongs to u. Is it is this function a differentiable function? This is a continuous function that you already know. That constant functions are continuous, that you already know. Now we are checking whether they are differentiable also. We do not know that yet, right? So let us try from the formula. So what we need to do is fix some element a belongs to u and look at this limit h goes to 0, f of a plus h minus f of a by h. So irrespective of what the point is, this is 9, this is also 9, 9 minus 9 is 0. So this is actually 0 by h for every h, and this is 0 function. So limit of a 0 function is 0. So this is equal to 0. So irrespective of what point you are taking, this function itself is a 0 function. Forget about the limit being 0 or not 0. This function itself is 0. So the corresponding limit is already 0. So this says constant functions are differentiable with the derivative being 0. So f identical equal to say 11. This implies f dash of a is 0 for every a belongs to u. Now in particular, for the function f is equal to 1, we should have f dash of a is 0 for every a belongs to u. Now previously I said we were looking for the derivative for formula for this. If I already know 1 by f is differentiable, so let us take a function f where this makes sense and this is differentiable. Consider the product of these two functions, f times 1 by f. What is it? F times 1 by f is identity function, right? So because two functions are same, their derivatives should be same. So f times 1 by f derivative at a point a is derivative of 1 at the point a. Just now we have seen for constant functions the derivative is 0. So this is actually 0, this is actually 0. We know what is a derivative of product of two functions. F times g dash a is a f of a derivative of the second function plus the value of second function times derivative of the first function. We have this to be 0. See, why did I ask that 1 by f is differentiable, that we should know before? Otherwise we cannot apply the product formula. F times g dash a, to write down that formula we should know a priori that g is differentiable. Here if I do not know 1 by f is differentiable, I cannot talk about this component. This may exist, but I do not know. If nobody told me that it is differentiable, I do not know whether this exists or not. Now the question is, if somebody says that it exists, then can you compute? That is the question. So now this is what, f of a times 1 by f dash of a plus this is 1 by f of a, and this f dash of a by f of a is equal to 0. So 1 by f, the derivative at a is equal to this is going here. So there is a minus f dash of a by f of a, and there is f of a component multiplying by this. So if I want to remove it, move it to the right hand side, it should come in the denominator. So this is f dash of a by f of a square, there is a minus here. So observe that these two are same formulas, 1 by f dash of a is equal to this. That's what we have shown here, right. So this is nice thing about differentiable functions. Sometimes, not always, sometimes if you know that function is differentiable, there is a slight chance that you will be able to write down the corresponding derivative also. Here in case of 1 by f, we have seen that nobody told me what is 1 by f dash of a. Just by the previous formula for derivative rule for product functions, we have concluded that 1 by f dash should be just this. So now what we have covered is what is a differentiable function, and one example, just one example, we will do some more now. And then we have seen the sum, the difference, product, multiplicative inverse are of differentiable functions are differentiable function, and we also seen we have also mentioned the formula for those the corresponding derivatives. 1 by f dash is this, and f g dash a is this, f plus g dash a is this, f minus g dash a is this. Now we will do some examples, and then we will stop the session for this time. In the next session we will see some more properties of differentiable functions. So now we have seen only one example, that is a constant function to be a differentiable function. So let us take the identity function. F of x is equal to x for every x belongs to u. Is it a differentiable function? So further what we want is the following: limit h goes to 0, f of a plus h minus f of a by h. We want this limit to exist. After fixing a point a belongs to u, we want this limit to exist. But see, this is a constant function, this is a this is a identity function. So f of a plus h is same thing as a plus h. So limit h goes to 0, this is a plus h, this is simply a by h, this gets cancelled out. So limit h goes to 0, h by h this also gets cancelled out, and we get the identity function. So there is no h component here. So limit of identity function at this point 0 is just 1. So the derivative of identity function at any point is just 1. So f dash of x is 1 for every x belongs to u. Suppose I am taking the function 2x. 2x is the function, it is not identity function, there is some slight change. Now what do we do? F of a plus h is 2 times a plus h, so that should be 2a and 2h. F of a is 2a, still these two gets cancelled out. Now I have 2h by h, right, this is what we are left with. Now I have 2h by h, again h's get cancelled out. Now we have a function that is still constant but not 1, now it is 2. So the limit of that should be again 2. So this says limit of identity function exists, the derivative is just 1, limit of identity function multiplied by any scalar is differentiable, and the derivative is just that scalar. 2 we are calling it as scalar. F dash of x is 2 for every x belongs to u. It can be any real number, any real number A belongs to any real number A is not the same A, we are using A for element of U, but for any real number P, say P is a real number, for any real number Fx equal to Px, then F dash is F is differentiable and F dash x is just P for every x belongs to U. The result is not dependent on the point. Now this is nice. Let us see we have already shown before that if I take two differentiable functions, their product is differentiable. Here I have said that Fx is equal to x is differentiable. This we have already said. Now product of this with itself should be differentiable. So f of x, if I x times x, now not the same f, say f tilde x times x should be differentiable. This is what x square, right? Now what is the derivative of this? What is f tilde dash, say at a point A? What is this? This is a derivative of this function at the point A. This is 1 for any point. So this is 1 times value of this function at the point A. So that is A plus value of this function at the point A, that is simply A, times derivative of this function at this point A. This is the identity function, the derivative is 1 with respect to what point you choose. In particular for this point the derivative is 1. So this is A plus A, that is 2A. So if you take arbitrary point x, the derivative should be 2x. So this says even the square function is a differentiable, the derivative is 2x. So one can just proceed like this for you can use induction, binomial theorem, whatever you want to use. You can prove that Fx is equal to x power n is differentiable at every point in the domain, whatever domain you take, and then the derivative also it is easy to compute. It is not 2x for every function for every x power n, it will depend on what n you choose. Now yes, so that is all about this session. So we have seen some examples of differentiable functions. We have seen first the notion of differentiable function, then some examples, then we have seen that how do you construct new functions from old functions, new differentiable functions from old differentiable functions. If I take two differentiable functions, the sum is differentiable, I know the derivative, the product is differentiable, I know the derivative, the difference is differentiable, I know the derivative. If I take a function that is nowhere 0 and I know it is differentiable and I know the derivative. So that is all for this session. In the next session we will see some other properties of differentiable functions.